So our second speakers today are both from TestSolve with a combined presentation, Ishwar Krishnan and Savita Suresh. The topic is formal verification. Ishwar has 6 years experience in design verification and has worked with both ST and Renesas. Savita has 3 years of experience in verification. Again, working with Synopsys, TI, and Renesas. Okay, so over to you, Ishwar, please.
Yeah. Hello, this is Ishwar Krishnan. Yeah. We are going to cover some issues we faced during form verification and how we were able to manage the issues. These are the three agenda. I will be covering a top level module selection, lack of assumptions, simulation and cover scenarios covered, long runtime assertions, multiple hierarchy used SVA divided into multiple SVA. Savita will cover catching RTL bugs with Jasper coverage, memory issues with Jasper solutions. Here are the first topics, top level module selection. Here we have two type of module selection, topmost module, sub module. This okay. This the first one, the topmost model of the design taken as the top level module. The second one is taking the sub model of the design is top level module. This diagram shows a typical DDR controller which has the AXA arbiter to arbitrate multiple CPU access. The request queue to store valid AX request, catch a control to check AX request, catch a hit, catch a miss status. If in case of catch a hit, catch a controller generates catch a memory read request. For catch a miss AX request, it generates DDR memory access request. This scheduler schedules the type of request like DDR write request, read request, and DDR refresh request with priority. This memory controller manages the physical interface between the DDR controller and the DDR memory. If the top mode model taken as the top model level, here we have AX interface. This here we will checking protocol random transaction scenarios and 5 interface interactions will be verified here. If we take catchy model taken as the top level module, it's like we are taking here sub model as the top level module. Here we will be verifying only catchy functionalities like hit AX request handling, miss AX request handling, DDR memory initial training request handling, and handling acknowledgements from different blocks will be verified. If we take this scheduler module as top model in the formal verification, here we will be verifying scheduling functionalities like DDR write request scheduling, DDR read request scheduling, and DDR refresh request scheduling will be verified. Okay. If we take Pi controller's top level module, here we'll be verifying sending acknowledgements to the catcher controller, and 5 interface interactions will be verified. This is the typical DDR controller. So in topmost model approach, highest level model of the design taken as the top level module. So we will be verifying system level behavior and interactions. If we take but in sub model approach, a specific submodel of the design taken as the top model level, properties related to this particular functions blocks subsystems will be verified. It helps analyzing specific behaviors or interactions without the complexity of the entire system. Yeah. This is the first topic. Now I'm going to change to the next topic. Next topic is lack of assumption. The next topic is lack of assumptions. Whatever assumption we are coding, right? That's the assumption represents properties that the design should satisfy under specific conditions or scenarios. To check this, we are writing the assumptions. The assumptions are constraints. Assumptions represent the characteristics of the design, input to the design, or behavior of the environment in which design operates. When assertion fails in formal, there are two reasons for it. First reason is all required assumptions were not done properly. Second reason is design behavior condition were not met. Were not met. So let's consider an example. Consider this below assumptions were not provided by the designer. These assumptions were related to catch controller model. Assume this catch dirty constraints that this catch dirty minimum register value always less than catch dirty maximum register value. The second one, assume one hot this assume constraints that only we will having a lot of channels, so we will be getting acknowledgement from any one of the channels. So there is no chance to get two or more acknowledgement at the same time. So if let's say we are missing these two assumptions in while verifying a catchy model, so that time the most of the checkers related to this catchy functionality will fail in Jasper. But this is not a design issue which we need to reported, but we have to check all the input signals and the catch conditions related to this catch data functionality. Then we once we debug all these signals, then we will come to know that we were actually lacking an assumption. This way we can find the failure reason, like we are missing some assumption. This is the second one. Yeah. Now moving to third one. Sorry. This is to address these assumptions. We have to follow these steps. First, we have to identify the assumptions implicitly record the properties being verified. Then we have to explicitly define these assumptions as a constraint. Then we need to ensure that assumptions accurately reflect the expected behavior of the design. Then once we find that, finally we need to verify the design satisfies all the assumptions whichever we coded explicitly that are all under all relevant scenarios. These are steps we need to make sure that we were explicitly coded all the related assumptions. Yeah. The next topic is like we are covering simulation uncovered scenario. We are covering in formal. Let's consider a scenario where the cache is being accessed by multiple CPUs concurrently. This property, this cache accounts property checks if we do read and write on same address continuously without any time delay. The read data should be equal to write data. Here we are not having we may have we may have the test scenario for this in simulation where CPU1 writes data to a specific memory location followed by CPU2 reading the same location. Even we can verify this in simulation. Simulation might verify the scenario successfully if timing is correct and the test simulate trigger the necessary events in the correct order. But in here the simulation we need to make sure all the needed monitoring logic taken care properly. We need to control write all the monitor logics and we need to make sure those are taken care properly. But while doing this, but there could be a scenario that simulation might miss, such as the rare conditions and interleaving between CPU access that are not covered. It's like CPU one and 2 continuously keep on reading same address continuously without any delay. If this type of scenarios could lead to potential catchy coherence violation, so that may go unnoticed during simulation. Like say for example, same example, like what I told before, this APB if formal property verification and scenarios identify scenarios when CPU1 and 2 access the cache continuously, uh, leading to unexpected cache state or data in condition that violates the cache coherence property. It's like in simulation, there is a delay between a single EXE transaction to another EXE transaction. But in In formal, we can create without any delay with a number of scenarios. So at that time, we may get some unfinded bugs. The state cannot be, maybe the state's going to unpredictable states. So we can find out more bugs like in this way. So by leveraging formal property verification alongside simulation, the verification engineer can complete the strength of both methodologies, ensuring comprehensive verification coverage and exposing the potential issue that might be unpredicted. So yeah, by doing both simulation and formal verification, we are increasing the possibility of verification assurance. And the next topic is how we can. There are scenarios. Some checkers will run for long long time. How we can analyze those assertions. Analyzing interactions and behavior of different hierarchy requires a free tool to explore vast state space and to contribute to longer verification scenarios. It's like here, if you see here we have taken different hierarchy signals, so it will take long time to verify this property. When assertion has different hierarchy signals to verify a design scenario, in simulation, we were creating a particular type of input scenario. So this type of assertions might go to active state or sometimes be at inactive state throughout the simulation. But in formal, it tries to generate all the possible combinations from all hierarchy. So it will take long time to verify the property. Sometimes it takes 1 week, sometimes it's keep on running. This is some example. Let's consider typical. This is a typical DDR memory controller. Consists of high performance bus arbiter, controller core with cache support, scheduler, and a PI controller. This cache request property has different hierarchy signals to verify cache unhit AX request to access DDR memory data. Here, this AXA command Q stores AXA memory address AXA memory data read request of particular address. This cache buffer checks the particular memory address data there in the buffer or not. This controller generates DDR memory read request or cache buffer memory read request based on the cache buffer hit flag. The scheduler schedules DDR memory read access request. So once this command queues DR valid asserted, then cache buffers no hit flag asserted. Within 1 clock cycle, cache controller's miss signal will be asserted. Then this scheduler should schedule DDR access request within 2 clock cycles. So this is here we use a different hierarchy. So the formal tries to generate all the possible combinations from here also we have a lot of combinations. This will generate all the combinations inside this hierarchy. So all the hierarchy will be possible will be generated. So it will take long time to verify the property. The next topic is how we can overcome this the long run time. We are using multiple hierarchy used SVA divided into multiple SVA. Yeah, to overcome previous long run time assertion, we can divide the property into smaller SVAs, targeting specific hierarchy or components. We can simplify the verification process and focus on verifying one aspect of the design at a time. Yeah, this approach allows us to manage complexity of the verification properties across multiple hierarchies more effectively and leading to faster verification. Here, for example, we can take the same catch miss request property. Here we are splitting the same single property into two properties. This DDR read request miss check one property was checking only AX request queue DDR value asserted and cache buffers no key asserted. Then within 1 clock cycle, clock controllers miss request should be one. The second the second checkers, this DDR read request miss check 2 checks only when this miss request 1 asserted. Within 2 clock cycle, the scheduler should schedule DDR memory access request. So this way, by dividing property into properties like this, we can easily verify the scenarios with less runtime informal, and when this lead us to faster verification. Yeah, I think for this next topic, Savita will continue on this catching RTL buffer bugs with Jasper.
Yeah, so let's see catching RTL bugs with the Jasper. So basically, the formal verification ensures the correctness by mathematically proving that a system or software meets its specifications, eliminating ambiguity and interpretation errors. So it can uncover subtle bugs and vulnerability that may not be easily detectable through traditional testing methods, that is a simulation. So leading to more robust and reliable system. So insert assertions into the RTL code to capture design bugs. These assertions act as a checks during the formal verification to detect the violation of the desired properties. So analyze coverage metrics to ensure that your formal verification tests cover sufficient portion of the design's functionality. So this helps in detecting corner case bugs that might otherwise go unnoticed during the simulation. So when formal verification detects a violation or fails to prove a property, so use a debugging features provided by the verification tool. So in that, one of the feature is called hunt command. So if you use the hunt command, if your property or assertion is failing, so it will take a while to prove or fail a particular property or assertion by using the hunt command. So so next see about the coverage. So coverage gives the formal users matrix to measure the progress and achieve sign off. So coverage extracts and displays valuable progress metrics, even for bounded, that is the incomplete probes. So it will helps to avoid over constraining the DUT. So like simulation coverage, Jasper formal coverage provides the support for both code and the functional coverage, including the cover groups. So formal specific coverage types provide data on what coverage is being exercised by the formal test bench, and well as the completeness of the formal checks. So Jasper coverage has the ability to generate custom reports and file formats such as a HTML and the text. So one of the format I have collected over here. So you can see the instance name and what all coverages we can capture in coverages, that is a formal coverage, stimuli coverage, and checker coverage. So along with the coverage also we can see if you are or if the user is excluding any cover, so it will show. If we are excluding any covers, it will show the numbers like how many covers we have excluded in a particular instances or a particular module. So when it comes to the formal coverage, so formal coverage it shows the percentage of covered and checked items. So based on the checker settings with the total cover item. So basically the this formal coverage is a combination of the stimuli coverage and the checker coverage. So when it comes to the stimuli coverage, it shows the percentage of covered item with the total cover items. So mainly it deals with the statements present in the code. So when it comes to the checker coverage, so it shows the percentage of checked i- uh, checked items based on the checker setting with the total cover item. So it mainly deals with the properties and the assertions. So this is what the coverage in terms of a HTML. So the same coverage we can capture in the text format as well. So going to the next slide. So while capturing the coverage, we may face the memory issues with the Jasper, and for that issue how we can overcome. So basically, in formal verification, based on the design size, formal tool will exercise the design exhaustively with the required more memory, which leads to the memory issue. So while capturing the coverage percentage of bigger design, there are possibilities to get the memory issues, and tool will not be able to collect the entire coverage database. So again, which leads to the incomplete of a data. So whenever you face the memory issue in formal using the Jasper, so like this you will be getting the errors or a warnings saying that you are left with a particular memory, so which will not be further collecting any coverage database, so it is totally waste. So before capturing the coverage, better make sure that we are specifying proper uh, p- perfect memory size. So how we can overcome this memory issue is, so user can avoid the memory issues by specifying the required memory size based on the design complexity as follows. So this is the set ProGrid shell. So here we have to specify with respect to our design how much memory size is required for to collect the coverage database. So here for particular design, for example, here I have specified 32 megabytes. So where M represents the specifies the memory size. So by specifying the memory size, we can avoid the memory issues in the formal verification. So this is all about memory issues. Yeah, thank you.
Yeah, thank you very much, Ishwar and Savita. Just seeing if there's any questions for you. We got 1 minute left. Just quickly, did you what would you say are the best types of designs to apply this to? Did you have an experience of which is your preferred type of design? IP, SoC examples. Savita?
Sorry, Mike, can you come again?
Yeah, so where have you applied this? Have you applied it at IP level or SoC level? What's your preference of where
Yeah,
this is best applied?
yeah, the formal verification is a best for only for the IP level,
Okay.
because SoC we will be having a huge design, so it may not be supportable. So IP level we have worked on.
Yeah, thank you. And that agrees with our previous speaker, Raj from Marvel. He says
Yeah.
exactly the same thing. So it's,
Yeah.
I think we're understanding the message that's coming through on that. So thank you very much, Savita. Thank you very much, Ishwa.
Yeah, thank you.
And thank you.